go ahead, Ricardo. Thank you.
Okay, so thank you again, Johan, for the introduction, and thank you everybody from Sheffield Hallam to hosting me here today. The focus of my presentation is very aligned with like my current affiliation and my research interest. So we will analyze what is what are the promises that robotics can bring to the agriculture domain, mostly for like fighting a shortage of labor in the field, but also it will allow us to address our, let's say, long-term plan of reducing the dependency on chemicals, or also targeting net zero goals. So this is like the overview of my presentation, which I really hope that I will be able to stick and condense in the 40-45 minutes that have been given to me. Very quickly, I will just describe the agri-robotics research we do at the University of Lincoln. Then I will provide a panoramic overview on the soft fruit industry, specifically in the UK, but it applies to more or less all the world, as a background and motivation of why we should bring robotic solution into the agriculture, and which one are the drivers for this adoption. Then among the robotics task, this presentation focus on the mobility and autonomy, because it's what I'm doing. So I'm not a perception or a manipulation guy. So I can provide my own story with also the European Horizon 2020 Bacchus project as a use case of where we deploy robot, what we are doing with it, and what is the long-term plan for robotics in the agriculture. In the end, if there is time, we will see some of the challenges and barriers that currently do exist and prevent the let's say the mass adoption of the robotic solution in the outdoor world, and more specifically in the agriculture. So for the background, Lincoln is quite famous internationally when it comes down to agri-robotics. We have two big research groups that are somewhat intertwined one with another, by bringing expertise on crop care, harvesting, logistic for the outdoor world. We won a few years ago a quite big grant for establishing this Lincoln Agri-Robotics initiative that, as I was saying, was like trying to group experts from different backgrounds, from mechanical engineering, from crop science, from computer science, into a single place with the focus of targeting net zero between here and 2050, and solving some of the challenges that are associated with the agriculture. Together with Cambridge and East Anglia, we also have a CDT Agri-Forwards that try as the objective of meeting 50 PhD students specialized in this domain. Yeah, and so in a way that they are going to be like the future leader in this sector and can drive the innovation in this specific subject. And out of our research group, there is also this white paper written by Tom Duckett in 2018 that was offering a panoramic overview of the challenges of agriculture as a field, and how robotics can sustain and help the development, the technological development of agriculture. But also more recently, Simon Pearson, director of the Lincoln Institute for Agri-Food Technology, brought this horticulture review for the British government that tried to identify what are the barriers for the adoption. So the reason why we are so efficient and so, let's say, successful in developing agri-robotic solution is because we have our own campus. Well, it's one of the two campuses which the University of Lincoln is divided. The Horizon campus just outside of the city that offer large open fields like animal farms, robotic fruit farm, where we can actually develop and test in-house any solution that we are trying to develop. And funny things, we also grow our own fruit and vegetable, which is locally sold. So this is for what it comes down to the agri-robotic side, but everything is backed up by the Lincoln Center for Autonomous System, which is a cross-disciplinary, interdisciplinary research group that brings academic and expertise from various domains, and they all work together to be, let's say, to establish as a concrete reality on the European international landscape. So in this graph, you have the list of our academics, and each of them is actually linked to the topic they are more keen or more expert to work in. And for example, I'm here and I have background in mobile robotics and AI and reasoning, and other people have expertise in something else. So I was saying that we tackled the problem of like soft fruit industry as to identify what are the driving forces for adopting robotic solution. With soft fruit industry, we identify the production of strawberry and raspberry or any sort of berries, which are actually very valuable. They represent a very concrete and consistent economic value. You can see, let me use the laser point here in the map, that the production is spread quite across the entire globe, apart from Africa and South America. But from the pie chart, we can see that the US and China represent together most than 0.5% of the global population, while the UK only is counts for 1.5%. However, like the data say that within our country, within the UK, soft fruit production represents 1/5 of the entire food production, and there's an economical value of 630 million, just like a few years ago, meaning that it's still quite an important market that we can investigate. And going deeper into the number, we can actually transform like the production of this fruit into how many robots can actually automatize this process. And has been forecasted that if we want to have like fleets of robots in which every single robot can have an harvesting production of 30 tons per year, we would need to have like between 3,000 and 5,000 robots just in the UK to sustain this market. So if you project this number on the world scale, it's easy to understand what is the potential of robotics in the agriculture in general. And in this case, just like with a focus on the soft fruit industry. So the margin of improvement, the margin of interest are really, really high. Strawberries are actually planted across the world in a very different way. Like in US or like in the country where the temperature is quite mild, that can be planted over the field. But like in the UK where the weather is quite rigid, they grow usually inside the polytunnels and sometimes on top of tabletops. This sort of, let's say, infrastructure, which is visible here on the right, actually serve also to accommodate the needs of the labor and to reduce their physical fatigue. But on the long term, you can see how a structure like that one tends to be quite nice and adoptable also by mechanical solution, because we would, and in the end is like what we actually have, we can take advantage of this like a corridor for having robots that navigate up and down, like inspecting the crops and like proceeding with the harvesting. However, from this image is also quite easy to recognize the difficulties of such job, because you may see here that there is a lot of fruit that are actually grouped together, and some of these strawberries are more ripe, some other are unripe. So the human has a sort of critical thinking that he needs to put in place to understand which out of so many strawberries needs to be harvested and which not. So it's actually easy to understand that the transfer of this technology from a human or rational agent to a robotic solution is not straightforward. So coming to the drivers for adoption, as you may guess, the shortage of labor is quite common. It's the main key factor. It applies not only to the UK, but to the entire world, because it's a very difficult job. It's time consuming. It can lead to physical injuries and is usually not very well paid. Usually is a job that is done by seasonal workers that migrate over spring to different European countries, and at the end of the harvesting season, they can go back to their own country. This problem became even more important in the UK after the Brexit, when people now, let's say other European people, in order to come here and carry out this job, they need to apply for a visa. And there's been a decrease in the number of applications that have been submitted, also a decrease in the number of applications that actually have been granted. So in the last 10 years, if you go and talk to farmers, you may actually notice that there's been a change in perspective, a change of narrative, when before people were seeing robotics as a way to take the job away from them. Now the farmers see the robots as the only way for them to continue to have a farm and continue to have a job, because they will actually replace or support the existing fruit pickers by robotic solution. A similar way, I don't want to say less important, still like a critical point, is actually the sustainability of robotic solution. Because, for example, until 20 years ago, there was like a mass adoption of chemicals, herbicide, pesticide in our fields. And now people are a bit more, let's say, rational or empathic about why we should stop doing that one, and we should find a better solution for taking care of like weeds in our fields that actually do not impact or minimize the impact that they have on the crop production. And in similar way, the adoption of electric vehicles, such as the robot visualized here, instead of fuel-based machinery, it can actually bridge the gap that we have between us right now and the long-term reduction of emission when it comes to CO2, or also achieving net zero emission target that I think is, yeah, I don't remember exactly which year we have in the UK, if it's like 2030 or 2050, but yeah, we are all working towards that goal all together. So robotics can actually be used in the fields for like targeting a large variety of application, from like fruit picking, harvesting, also to just like logistic transportation, which is the problem we are trying to, I will describe later in this presentation. Robotics come as a umbrella term that identify a large variety of tasks that is like the autonomous navigation, but also a safe human-robot interaction with the fruit pickers in the field. There is a coordination and collaboration of multiple robots in the field, but also the harvesting itself. How we can identify a crop and can grasp, harvest a specific fruit product without damaging the plant or unripe crops that are nearby. And in Lincoln, starting I think in 2017, we had this massive umbrella project that we call a Raspberry, which comprised multiple little projects, each of them focus on addressing one of the bits, one of the sub-problems that I described before. So that was like a sort of collaboration, a joint effort between us as academics, some other academic partner, industry producing, for example, this specific device, but also local farm that are working or in Lincolnshire or in Kent. So at the basis of deploying a fleet of robots in the field, there is always like autonomy. And in particular, we developed this idea of topological representation of the field, because differently from an indoor environment, it's very easy in the field to identify some corridor along which the fruit picker actually are located and go up and down. And we can actually build a robotic map for deploying the robot that take advantage of this geographical representation. Having done this, we can actually take advantage of this representation for properly representing the robot, so properly localizing the robot on this map, and defining some intelligent and efficient path planner that try to minimize the travel distance between a robot and his destination point, but also some task allocation algorithm that coordinate a fleet of homogeneous or heterogeneous robot depending on the task at hand. And having said so, our idea that we try to do as part of this Raspberry project was to create a sort of smart farm where human labor fruit pickers are actually entitled only to do the picking of the fruit, and then the logistic was left to the robots. They were actually navigating between the pickers and some like storage location where I don't know, we have like cold storage where the fruit is actually to be stored, because every hour that they spend in the field, there is a decrease in value, or like a sort of like warehouse where also the robot can actually get their battery charge or whatever. And everything is gonna be, let's say, managed using IoT technology or like 5G and whatnot. So yeah, I was saying that the focus for mobile autonomy is actually to assist the pickers, because I've been found that 20% of their time they are not exactly in the field, but they are moving the harvested product between the field and like a storage area. And doing that one, they are actually obviously reducing their productivity, but they are also subject to physical injuries. So the robot can actually came and play a role into this picture, trying to increase the productivity of the entire farm while also preserving some of the let's say physical skill of these people. And in these slides, I put like two examples. One is like from our local farm, let's say at our agriculture campus that I mentioned before, and this one is UC Davis in California. And here now we have this sort of solution that I will describe soon, where like we have a fruit picker along a polytunnel that finished he basically finished to fill a tray with some harvested strawberry, and he called a robot that autonomously from wherever he was approach the person. At this point, the person can load the tray, the full tray on top of the robot, and then he can like press a button and send the robot away. So the robot at this point, he will leave the fruit picker to continue carry out his job. He will go to a cold store facility where somebody else will unload the tray from the robot and will put it in a refrigerator. And this solution with different technology, as I was mentioning, was implemented also by at the UC Davis University. So I was mentioning this topological representation of the map where the robot can actually traverse, and he knows, apart from the definition of this map, they can actually be organized as a multiple level hierarchy where every map can be associated with a specific task. And in this case, we have like a quite fine representation for a logistic, meaning that this map is, for example, used by single robots to go and collect trays, while this other map, which is a bit more sparse, a bit more coarse, is used by a different topology of robot for UV treatment, that, for example, overnight, they go with UV lights and treat the strawberry in order to kill any disease or little animal that can be fly around. And the idea is actually to move from a situation where the maps can be used only for moving the robot to a situation where a person can actually call a robot and the robot get there and carry out some job, and then it goes away. In order to do that, we have to create some interface that we call a Kela robot and a Senda robot that have been implemented as a mobile app that a picker can actually have on his smartphone. And the moment that he finishes his task, he press a button, the robot will get there, and so that the picker can move the tray on top of the robot and then get a new one. In order to do that, in order to actually a robot need to identify a picker, we need to be able to localize where the picker is located in this sort of topological map. The problem we have is that picker are usually associated with a GPS signal that can come or from their mobile phone or from this device that we usually locate on the top of the tray that the picker use for their job. But GPS signal, the standard one, so not the RTK one, it's very cheap, but at the same time it's very noisy because the accuracy is quite high. And the problem is even more pronounced within the polytunnel because they have like a metal frame that actually can introduce additional noise. So using a standard localization approaches like a Kalman filter or particle filter doesn't really play well in this specific scenario because the robot is constrained by corridors that are, for example, 1 meter wide, and we cannot send a destination with a covariance I'll say not accuracy, the opposite of accuracy, an uncertainty that high. So our idea was actually, okay, we have the map, why don't we try to take advantage of this topological graphical representation for also solving the localization task? And that's how basically we come up with a new formulation of the one that we call internally topological particle filter, in which the particle, instead of being uniformly distributed over a continuous map, like in the standard indoor mobile robotics, they are actually located only on the nodes of this graphical representation, and they move between the nodes that are actually connected by an edges, following a transition model that is derived by the human picker behavior that move usually at sort of like a constant speed, but they have like this sort of pattern that gets repeated over time. And then, as in a standard filter, we can have a correction step in which we integrate data coming from 2D LiDAR or even RFID tags that are mounted or like located on the arms of the picker in order to better represent the position of this picker so that the robot can identify it with sort of like high accuracy and get there. So I talk about localization, I talk about navigation, and the technology that has been developed so far. He also found application in this European project that I was like co-leading until yesterday because he finished yesterday. It was a project that started in 2018 and he ran for like, well, we got an extension, so he ran for like 5 years now. And in Bacchus, we have basically a team of robots. We have like 2 robots that are assigned some different tasks. One is the one we call inspection robot, and one is the one for harvesting. So let's have a look at them in a bit more detail. So, okay, before that one, the Bacchus project is a European project involving 2 universities, actually 3, University of Lincoln, Thessaloniki in Greece, and University of Turin in Italy, where Lincoln and Greece focus mostly on the autonomy when it comes like navigation and harvesting. Turin mostly was involved in analyzing hyperspectral data coming from hyperspectral camera mounted on the robots. We have 2 industrial partners providing the platform used, and in the end, a stakeholder, the Team Major Vasilio Vineyard, which is among the top 5 wine producer in the Hellenic country. So I was mentioning the first robot is this Torval robot produced by Saga Robotics that is called inspection robot because it's equipped with perception sensor. Mostly there are 2 RGB camera at the front and on the side. We have a multispectral camera on the back to collect information from the side plants. We have 2 RTK GPS for high precision localization and a 3D sensor mounted on the top. And the second robot is the Vogi from Robotics, Spanish company, who is equipped with like two manipulators. And they have like 2 different end effector. One end effector, completely 3D printed, is basically has the objective of approaching the fruit and like keeping that bunch of grape in place. And on the second end effector, there is a cutter that as the objective, as the name suggests, to remove this bunch of grape from the plant. This one is a graphical representation. Basically, at the end of the project, we create like a GUI that is basically offered to the farmer to basically allow him to take into power like the operation of his robotic fleet. So on the left, we can see this image that is like it comes from a UAV. We can see the inspection robot that is traversing this row. Let's use this one again. It's traversing this row, and while it traverses, it basically identifies some grape of bunches of grapes that are actually mapped, meaning that are associated with like a specific spatial location into a map of the environment, and then the information on these grapes are actually stored into a database. When the operation of the inspection platform is completed, the data are straight away presented to the farmer that may decide that he may decide that it's time for performing the harvesting. So now you will see at the bottom left that the second robot, the harvesting robot, will start to move, and then now you will see it like in the video. This is the harvesting robot that start to move autonomously, and it will go in front of a specific plant in order to harvest it. So now it will traverse a bit, and then I will move towards the point of interest. And now you can see here that there's going to be this bimanual manipulation of the grape branch, in which the first and the effector on the left can keep the fruit into place, and the second effector with the cutter and an RGBD camera on the top will slightly approach the stem on top of the grape branch, and when it's going to be confident that the cut is going to be affected, the two blades will actually they will close, and it's going to be possible to remove the grape from the rest of the plant. Let's see. Okay, it was cut. The video was cut. Anyway, okay. So from the perspective of Lincoln, that like we are basically our expertise is in localization, is in mobility. We wanted to use this project to understand if it's possible within an outdoor environment. Basically, don't rely on RTK GPS, which is the de facto standard for when it comes to outdoor localization. The reason why we do that one, we want to do that one, is because RTK GPS usually relies on external infrastructure or external services, which can be expensive. So a local farmer may not have like economic power to afford such a service, but it still in some way depend on weather condition. So we would like actually to investigate onboard localization system such as a SLAM that allow to have all the computation are running on the robot, but they also offer fully autonomy because they allow to answer the problem of obstacle avoidance, such as there is a fruit picker in front of the robot needs to stop, and a problem like that one cannot be solved by using only the GPS signal. And another interesting bit of like deploying robots outdoor and in the agricultural environment is that there is a very drastic change across the month and the season of the year when it comes down to the same environment. So we can see, for example, here on the right, this is basically a snapshot taken from the very same point in 4 different months of the year, actually across only 2 seasons, which is like spring and summer. To be fair, if we were like in winter, like in December, I would expect these images to be quite close to March because the plants are actually sleeping. But it's interesting to see how the environment changed drastically. So we cannot really rely on previously existing map as we would do in indoor mobile robotics, because if we actually want to deploy a robot in June, try to localizing using a map built in the previous months, that would probably not work. And well, we brought a paper that said that it actually doesn't work. So I probably need to get rid of the conditional in my speech. So the first step that we identified to study this long-term evolution of the environment across the year is to create the first data set in the world that actually try to map the same environment multiple times across the year, so to capture this changing nature of the environment itself. So we deploy the inspection platform where with large variety of sensors that are all reported into this table for 10 sessions in 2022. Some more sessions have been recorded in 2023. Some other sessions have been recorded in Lincoln as part of our mock-up vineyard that we have. And we basically wanted to use this data to assess navigation and localization outdoor without the GPS. And in particular, we wanted, the research question we had was actually to, the question was like, can we actually extract out of raw data some features that are consistent and always present across the 12 months of the year? For example, having a look at these two images, we can see in March that there is quite a lot of artificial infrastructure given by vertical metallic poles and the water pipe that, even though is less visible, is still present in June. While the vegetation is present in June, but is not present in March. So is there a way that we can actually, given sensor data in June, extract only the points that are associated to the static features and use this information for localizing the robot? And the answer was actually yes. And so we come up with this sort of architecture that, for the sake of time, I will not discuss too much right now, where we basically, given a given map, we were able to understand which points are, let's say, spatially and temporally inconsistent, and with disregard all of the other. So having a look at this specific image, we can associate like a continuous label between a 0 and 1 for each point in a laser scan. And basically 0, it means that that object is static, is always present. And with reference here, we can see that in blue, we have, for example, the point associated with the ground. And at the top, we have like 1, which represents the full dynamicity. And in this zoom in, you can see that like the laser scan associated with a person is actually colored in red, because the points associated with a person are always changing, because a person is an object that is actually dynamic, is not going to be there all the year, and is moving. So we can filter out of a laser scan all the points that are, let's say, green and red, leaving only the blue. And we can actually localize a robot using this filtering observation against a previous map. And moving here, basically, we compare localization performances of filter information towards the raw information. And basically, we computed the root mean square error and the mean error over the absolute trajectory error. And we found that using this approach actually drastically improve over the raw data. So this is basically a close lookup of what it looks like. And basically in yellow, it's the raw observation coming from the 3D LiDAR, while in white are these filter points that I was talking about, which are the ones that are always constant, regardless the period of the year in which we are deploying the robot. And interestingly, you can see that the white dots that have been a bit thicker, so are they are more easy to be distinguished from the white, are associated with these vertical poles that you may have seen in the previous images, and on the water pipes that connect all the poles. And this is just like a video representation of running our localizer in the vineyard. The resolution should improve. But so basically, using this filter approach, we not only improve the localization performances, but we also noticed that we could solve the localization problem in some scenario where standard data would actually fail. it was observed, for example, localizing a robot only using 3D point cloud in the summer months, where the plants are very rich for when it comes down to foliage. Introduce a lot of visual aliasing, which was preventing the localization module to correctly doing the job. But filtering out all these points actually solve the problem. So is a step that we've done so far, and we are trying to improve to really achieve a sort of long-term, low-cost localization, high localization solution in the outdoor environment. Then very quickly, like the Bacchus project has some other tasks that we in Lincoln we didn't explore. It was like left to our partner. I was mentioning like Turin was like focus on identifying diseases, or like also the current analysis of hyperspectral, multispectral data. Some people were looking at diseases from visual images, detection of weed, or even creating the web GUI that we saw into action before. So I will conclude like my presentation for like the minutes that are remaining to me. Is the presentation, Johan, 40 or 45 minutes?
Yeah, you have 5 minutes more.
Okay, 5 minutes more. Okay. So probably I will just spend time only on these slides. We will see to identify what are the challenges that we still have to face. And the main one is actually bridging the gap between the academia and the industry at the global level. So what do I mean? Like in academia, there are a lot of research groups that actually try to tackle an individual problem like perception, harvesting, navigation, and they achieve a very nice result as long as these problems are tackled individually. But when you put like a system together, the performance actually drastically decrease, and the solution are not very robust. So it means that, for example, it works in the solution will completely overfit a scenario, but then we move it somewhere else and we get very terrible result. The usual question is like, who actually needs to fill this gap? Is it responsibility of academia? Is it responsibility of industry? Should they need to collaborate together? In general, Innovate UK projects are like quite nice in that sense, because they try to bring different partners together and answering this question that try to fill the valley of death. But this is clear, is still like an open question that we need to be addressed. From the perspective of the farmer, cost is also like a significant problem, because the sensor suite alone can actually represent 50 or even more cost of the entire platform, because maybe producing a mechanical platform is not that expensive, but adding a high resolution point cloud or camera sensor, and also the software required for processing this data can be expensive. We have the problem with the scalability. When we want to deploy multiple robots, these robots need to be properly coordinated, properly managed. And sometimes we also may need to modify the infrastructure of an existing platform, an existing farm, in order to accommodate the deployment of the robot. So this one is another problem that is quite linked with the cost. And in the end, which is quite important and is not regulated so far, is how these robots should behave alongside the human, or how human should actually behave alongside the robot. HRI is a quite important subject that is underexplored when it comes down to agri-robotics. So also in this case, further exploration needs to be done. So I will skip like these slides that try to go deeper into each of these problems, and very quickly I describe some of these problems that are a result of this horticulture review that Simon Pearson, which is the director of the Lincoln Institute for Agri-Food Technology, wrote for the British government last year, and identify what are like some other barriers that prevents robots to be adopted. In particular, coming down to bridging the gap between academia and industry, there is still like quite a indifference or lack of confidence from the private sector in investing in this solution, mostly because there are not so many successful stories that really prove the point. So there are some nice demonstrators, but on the large scale, there is still no a big company, and this one probably covers the third point. There is no big company that is trying to draw the line about how this sector should evolve from now in like 10, 20 years. We have a lot of small startups that they try to reinvent the wheel every single time because they basically develop something, they cover it with patents. So any solution needs to be, any problem needs to be targeted by all the each individual identity. And as Lincoln, we try to solve this problem. We have, from the software side, we have a recently started project called Agri-Open Core, funded by Innovate UK, which will try to create a new navigation, a new robotics software robotics stack, completely open source, that industrial entities can use and build on top of them. So we will basically provide the basic building blocks for doing harvesting, for doing perception, and then the companies can actually take it from there, improve it, patent it, and that's it. There is a problem with business model. It's still not clear if farmers want to buy robot or use the robot as a service. So maybe they will rent it out for the month, for the season, whatever. And more importantly, and maybe as a Lincoln, we are going in the direction, is there is a lack of expert or young researcher in this domain. So for example, our CTT AgriForwards go in the direction of creating 50 new PhD students that are going to be the future leader in shaping this world. But more effort needs to be put, maybe not only from the UK, but at a larger scale, because agriculture is actually a more advanced field than what people may generally think about, and it's important for every single country. There is no country that doesn't spend the money and resource in agriculture. So it's important that every country has people expert in that domain. And on the long term, and this is really the last things I want to say, is that probably we won't see robots that do autonomous and efficient selective harvesting in the near future. That is still like very far from now, given all the problems that I described so far. But maybe the first thing that we can do is actually providing IoT, AI, robotic solution that try to augment the efficiency and the job of the farmers, of the fruit picker, by offering some additional investigation tool like a crop care, logistic, or even forecasting. So yeah, was like the end. I thank you again for having me here as part of this seminar series. I know that maybe I may have rushed a bit on some of the slides, but we have like 15 more minutes to answer some of your questions. So yeah, it was a pleasure for me. Thank you very much for listening.
Yeah. Thank you, Ricardo. Thank you so much. First of all, I would like to extend my sincere thanks and gratitude from the Hallam community itself, on the behalf of Hallam community, for this engaging and informative presentation on mobile robotics in the agricultural domain, particularly the insights into the challenges which are faced by the agricultural industry and the transformative solutions you guys are working on in Lincoln. Most importantly, I would say that I particularly appreciate the way you have conveyed these complex concepts in a very clear and accessible manner to our general crowd, which do not have much, I would say, background in agricultural robotics or from the domain of mobile robotics itself. So we have a very multidisciplinary crowd here, where the students are from automation, control, robotics, and several interdisciplinary domains itself. And the examples and case studies have been instrumental. Basically, they have enlightened me and all of us here on the implications of integrating these mobile robotics into agriculture. So thank you for that. Thank you for shedding light on this crucial topic and inspiring us with the potential innovative solutions you and your team is working on. Your expertise is basically evident throughout this presentation. It has a very lasting impact on, I believe, all of the attendees in this presentation itself. So I would open the floor for the questions itself to my colleagues and all the students who have joined. So please help yourself with asking the questions. Any questions for our speaker?
Could I ask a question?
Yes, please, go ahead.
Hi, my name's Bija. I'm more of an applied mathematician. Thanks for your really interesting presentation. I joined it halfway through, so apologies for that. But I saw that your robotics was engaged in farming within the wine industry, and so at the moment are you kind of restricted to particular types of agricultural, farming that you can use these robotics? In particular, what came to my mind was farming of coffee beans, which are of a similar structure, the plants.
Yes, so thank you for the question. I will share again the presentation because I started by targeting the soft fruit industry, because that's how in Lincoln we basically started working in agri-robotics. So we have a large of expertise in strawberry detection, strawberry picking. So the vineyard is something that we only start to explore recently as part of this Horizon 2020 project, Bacchus, that I mentioned before. I would say probably 80% of our effort is in strawberry because it's quite financially important for the UK market, I would say. There were like some images like here where they say that, yeah, like strawberry is like 1/5, well, soft fruit is 1/5 of the entire food production in this country, with quite a big number when it comes down to money. So currently I'm working with vineyards. So the Bacchus project actually currently finished yesterday, but I'm involved in this Vista project with a wine producer in Oxfordshire. Because apparently we also produce wine in the UK. We will have good wine in few years from now, but because of the climate change, UK is seen as it can be like a key player in the next 30 years when it comes down to wine. So the DEFRA minister is actually quite interested in funding projects that are focused to wine in the UK, which is surprising, but is a reality. I collaborate with partners in Germany, in Bonn, that they work with apple orchard. I'm not very familiar with how a coffee bean plant look like, but I trust you that if it looks like very similar to a vine, there's no reason why the technology that we applied here cannot be transferred to a different sort of type of crop, especially because the technology we applied in the vines come from the strawberry.
Yeah.
So
could I ask you one more question? Because there might be other people who aren't interested in asking a question. I mean, I've seen Boston Dynamics, which are quite very advanced robots, which can take into account the change in terrain. And so I was really interested in your presentation, because although I can see the structure of the robot you currently have, do you see a possibility of adapting that to be able to take into account different terrain, which would allow your research to venture into a larger sector of agriculture? Of course, I understand you're interested and focused on the UK sector at the moment, but obviously, advances that you make will feed out into worldwide countries where agriculture is quite important, but they have a different type of terrain, such as a bit more rocky and
so there was no margin of exploration in this project, but there was an idea of, for example, using IMU data for estimating the terrain traversability, and based on that, we're maybe developing different navigation policy. Coming back to Boston Dynamics, to be fair, everything that they do is really control based, so there is no learning into it. So it means that the video are very impressive, but are very artifacts somewhat.
Right,
so
misleading.
If you take that robot and you move it to something else that is showing the video, is gonna collapse. The solution would be actually to learning some policies out of data, so that if you can generalize to previously unseen environments. So if actually Diro's robot would find a slope in front of him, it would slightly modify the control parameters of a PID controller in order I don't know, to give more trust or something like that. So yeah, there is margin for doing that one. I was investigated as part of a different project before jumping into agriculture when I was like studying traversability. But yeah, I agree, it's an interesting navigation challenge to tackle if we want to develop a sort of solution that can be widely adapted by different scenarios.
Yeah, great. Thank you very much for your answers. Thank you.
Thank you for the question.
Any further questions for the speaker from the attendees?
May I just ask one?
Hi, Ningrong. Yeah, please go ahead.
Thank you so much. It's really very interesting and inspiration presentation. I'm just wondering, is your robot being continuously trained, so learning from the new data inputs and then continuously improving itself? Or it has been pre-trained and then
yes, that's a good question. So the navigation is not learning based. I mean, literally just traversing the road is not learning based because there was like quite a robust navigation policy fine-tuned over the years, and we didn't want to break it and incur into like damages of the plants. The long term would be something like you suggested, like some continuous learning. We started from this very long data set that encompass a lot of information, and we got, let's say, our initial policy. But on the long term, I think what people want is that academics are not always there to refine a solution. So the moment you want to have a robot that adapts on the environment for the next like 5 years. So we don't do that, but I think that's the approach, the orientation that academia should have for targeting a large variety of problems, not only in agriculture not only in agriculture navigation, but for example, linking to the background of Yogang in marine navigation, you may want to actually take into account varying sea current, weather condition, and learning out of it. So to always provide a more smooth traversability of the ocean. So yes, very quickly, the answer is no to your question, but I think it's a valid input for future project where we can say, oh, we already achieved success story in the Bacchus. So the next things we want to do continuous learning.
Really interesting. Another question would be, does the fleet of robots, do they talk to each other in IoT setting and then can do optimization, such as like optimize the overall efficiency of the harvesting, etc.?
So the fleet management bit is not something that I was directly involved, but from my understanding, there is a manager on the back that collects the data, and then he does task allocation of robot to different tasks. So the individual robot are agnostic of the existence of other robot, and they depend on let's say a centralized workstation. They take decision on their behalf.
Thank you.
You're welcome. Thank you.
Any other questions from the attendees? I believe if there are no further questions, then maybe I can have the privilege of asking a few questions as well. One is related to the AI-driven your decision-making algorithms, which you are using in these mobile robots. That is generating a huge amount of data. So is that kind of data has been open sourced in a way that other universities who do not have access to such facilities can also utilize it for designing and developing some of the technologies and contributing to this this amazing mission you guys are on at the moment? So is it possible to have any access to this kind of data which is available in open source?
Yes. So as a research group, we really believe in open sourcing everything. And as I was saying, this new project that we have, Agri Open Core, they try to define an open stack for robotics in agriculture that can be used by other university or company, is a symptom of our policy. So depending on which specific topic you are interested, if you go like on the GitHub of our group, the GitHub of HealthCast, you will find, for example, topological navigation is the software package that basically define how robots should behave on this topology. There is like a wiki tutorial on how, starting from a normal map, you build your own map as graph and edges, how to define a policy that the robot needs to adopt along the edges, because obviously in some edges you want to go straight line, but maybe because these robots are also omnidirectional, at the end of the row, maybe we want to do lateral shift. So you want to implement this sort of like behavior. Also, the data set that we collected across 8 months is publicly available on our website. The publication we made out of it is associated with the link, so people can go there and like freely download the data. Most of everything we are doing is open source. Also, when we are like involving Innovate UK project, that's a bit more critical, because obviously there are companies that want to advance their state of the art, so they want to actually close with patent the technology, but we always try to get at least a publication to, I don't know, present the underlying idea and make the work reproducible by other people.
That's brilliant. That's brilliant. I think that's a very useful information for all our attendees, because many might be interested in this kind of data for their own research or for their any future research as well, where they can be interested in some effective integration into the agricultural ecosystem around Yorkshire itself. One of the final questions is that what considerations should be taken into account regarding the cost effectiveness and accessibility of implementing these mobile robots for these small scale farmers, or those in the developing regions who do not have this kind of larger money like vineyards or many other bigger farmers or bigger players have. So what considerations can be taken into account regarding the implementation of this kind of technologies for those small scale farmers or developing regions?
Yeah, that's an interesting question, because I also faced like some recent challenges when I was proposing a project to use low-cost sensor, because small players, maybe they still rely on a labor job for doing the harvesting, and saying, well, we cannot force these people to adopt RTK GPS that requires, for example, a fixed antenna to provide the correction and so on. And yeah, the people that come back to me say, to be fair, everybody use the GPS because it's used for a large variety of technology, which are also not smart, but also like tractor now are equipped with GPS for sort of like autonomously traverse the field. But tractor, I don't know. It's I think cameras are probably the future, because you can get a very nice camera for 300 pounds, and sometimes you also come with deep learning model that are already included for doing, I don't know, people perception, doing tracking, doing mapping, and probably the trade-off information you get for the cost that you put into it, it's very positive. But at the same time, the research of using camera compared to point cloud is still not on par. So yeah, I don't know, I probably lost a bit the focus of your question, but I really think that there should be, first of all, more effort from the researcher themselves to develop research that takes into account low-cost sensor. And on this line, it seems that like a radar is coming into play instead of LiDAR. And a radar is usually as a cheaper and as a simpler technology that so far has never been used on the field. I think a camera probably is something else that we should do.
Oh, yeah, the low-cost sensors indeed is a way to go forward with such technologies.
Yeah, because I think is the only way for assuming that like a local farmer with maybe the needs to sustain a local community has only, I don't know, 3 workers under him. Obviously, he cannot afford a robot that costs 100K. He cannot afford the big machinery. So we need to find a way that maybe it can be robot as a service. I still don't know. We need to make it affordable for the small player in the sector if we want to automatize the entire sector.
Yeah, and we were facing the same issue when we were a part of this Purdue Nexus consortium, where we were trying to solve some issues of pollution monitoring in agricultural water bodies in Peru, and we were trying to develop these low-cost marine robots, which are basically connected via IoTs, so that they can have a central database to look into different water bodies at the same time, and basically collecting water samples and sediment samples from the underwater bed, so that they can determine this long-term impact of mining on the agricultural food cycle within Peruvian highlands. And that was also a part of our work in my postdoc back in US as well. So I generally believe like we were developing these low-cost platforms for them at that time as well, because that was also a very bigger constraint for them in terms of the amount of money and the amount of effort they can. And I also believe the training of farmers is another aspect where I believe you guys are also working on to train them to work on these sophisticated technologies or to these advanced technologies as well, so they can operate on themselves rather than depending on academic or an industrial organization to do so. So brilliant. Yeah. So again, I thank you again for your time, for sharing this extensive knowledge, and I look forward, and I think we all look forward to staying informed on the developments in these exciting field. And I hope we have a further opportunity to invite you in person here at Sheffield Hallam and have your presentation and have your interaction with the wider community here at Sheffield as well. Thank you so much for giving us the time and giving us this opportunity to listen to this amazing presentation of yours. I wish you all a happy weekend, and I will get in touch with you, Ricardo, on on phone and have more chat with you. It's been a long time to since we had a chat.
Thank you again for inviting me. It was a pleasure to give this presentation to all of you. I don't know if I have to share like my presentation, but you will have like a way to contact me if you need any further question or you want to know more about the research we do in Lincoln. Thank you again to everybody for being.
Thank you all. Yeah. Happy weekend. Have a good weekend. Bye. Bye.
Bye.